Hi, I'm an old guy and I do maths. Today we're looking at nuclear decay, and in particular, how we go about finding K, the constant for an isotope, and this letter in this formula. So almost immediately I hope you can see that at some point we're going to have to resort to logarithms. There will be those amongst you who do physics and chemistry, and so I hope you will bear with me in this. There will be things that I say that you already know, but this is intended for a mathematics audience. I've adapted a problem that I saw in a mathematics textbook in order to do this. I've changed the numbers and I've extended the problem a little bit. Okay, so as I said, this is the formula for nuclear decay, and those of you who have seen other decay problems in mathematics probably might recognize elements of this. This is our starting mass for whatever substance we have, and this is what we wind up with. And as you can see, we're dealing with some sort of negative index here, so it's a fair indication that something is going to wind up smaller than it started out. Okay, so let's have a look at our problem. After 500 years, a substance is 37.2% of its original mass, so it is essentially its mass has shrunk. What is K, the constant for this isotope? So what I'm asking is, for the mathematicians and the non-physicists and non-chemists amongst you, is I'm asking you to find this. It's a made-up substance. I doubt very much whether there's an isotope that does what I've said here. As I said, I'd adapted it from a problem that I found in a book. Okay, so let's see what we know. We know what T is. T is time, and it's 500 years. So that's kind of important. And we know what our end mass is. It's 37.2% of what we started out with. So we can write A in terms of AO. So A is equal to 0.372, 37.2% of AO. And that allows us to fill out all of this formula save for negative K. Okay, or K with a negative in front of it. So let's do that. Now there are a lot of numbers and so forth flying around here, so I did this roughly on a piece of paper, and then I wrote it out as neatly as I could. I understand my handwriting is not the best. So 0.372 of AO, which is what A is equal to, is equal to our initial mass times 2 to the power of negative 500, which is T here, negative 500 K. Or we could go negative K times 500, but it's just easier to write it like this. Now, we've got AO on both sides, so basically we can, I suppose technically what we do is we divide both sides by AO and get rid of it. The net result of that is here. So 2 to the negative 500K is equal to 0.372. We are solving for an index, therefore we're going to need logarithms. So what I've done is I've rewritten this as a log, and I'll just explain that. So what this says is that 2 to the power of negative 500K is equal to 0.372. So our log is in base 2. And the number that we're looking for, the result we want, is 0.372. And the question is, what is the power of 2 that will give us this? So when you rewrite something like this as a log, your base is here, your power is here. And the number that you're eventually going to wind up with is here. So this is just a very basic rewrite. Now that means, however, that I can rearrange this. And that is what I've done here. So I can get k on its own. K is equal to log 2 of 0.372 divided by negative 500. The answer is 0.00285. So we have found k here. Okay. Now, normally that would end this, but I was intrigued. I actually did this just to make sure that my calculation was correct. I put this into an online calculator that does logs in base 2 because I'm an old guy and this is as technical as I get with calculators. And so this does log 10. It does natural logs, but I wanted to do this in log 2. This does log 10. And I thought to myself, well, what would happen if someone were in a similar position where they could only use log 10? And so I have an answer. And here it is. This is using a one of the many log rules that are around. You can write log 2 of 0.372 as the division of 2 logs, and you can select your base. So this is, you'll see this in one of my videos on the log rules. Okay, so here goes. Pop that into an online calculator, and I got negative 1.42662. I did this on my trusty $30 calculator from the convenience store, and I got the same thing. So log 10 of 0.372 divided by log 10 of 2 gave me that. Now, putting that into this equation, that value into this equation, remember this is what I got here. And again, you can check this on a calculator. In fact, I'll do it now. So it is negative 1.42662 divided by negative 500. So that is everything with the negatives in there. I didn't need to put the negatives in, but there we go. What do we get? We get what you see here, 0.00285. That is our value of k, and that is it done with logs in base 10 so that you can utilize a very ordinary calculator to do this. That's just a bit of a bonus. Now the next thing that we're going to look at in this series is we're going to go through the business of calculating k for a different but equally made up isotope. And then we're going to go on and calculate the half-life. So that will be the next thing that we do. It also involves logs, so it'll be in this playlist. Thanks for watching. See you next time. Bye.